Hello, my name is Mike West, and welcome to XGBoost Masterclass in Python. In the course, you're going to learn everything you need to know to be able to build end-to-end models using XGBoost in Python. XGBoost is an open-source machine learning library that belongs to a class of models called gradient boosters. XGBoost is a supervised machine learning algorithm. Supervised machine learning uses existing data to look for patterns. Two of the most common approaches when building supervised machine learning models are classification and regression problems. XGBoost excels at building highly accurate classification and regression models quickly. Because most applied machine learning is classification and regression, this means XGBoost is the top choice for building real-world models against highly structured datasets. Additionally, XGBoost has become the gold standard for competitive modeling. XGBoost has won almost every competition using structured datasets on Kaggle. To introduce some of XGBoost's powerful features, you're going to be using the Python programming language. Python has become the most used language for machine learning engineers in the real world. Additionally, we're going to skip the math in this course and focus on the programmatic elements of XGBoost. From an applied perspective, gradient boosting is a shallow field, and a developer can quickly start making very real impact using XGBoost. Thanks for your interest in XGBoost Masterclass in Python, and let's get started. In this lesson, let's define XGBoost. Before we do that, let's find out where XGBoost lives under our AI hierarchy. Recall that within machine learning, there are two broad categories of models. The first group is deep learning models. Deep learning models are artificial neural networks. The second group is traditional models. XGBoost lives under the traditional model umbrella, and that means XGBoost is a traditional model. All right, now we know where it lives. Let's define it. XGBoost is an implementation of gradient-boosted decision trees for speed and performance. XGBoost stands for Extreme Gradient Boosting. The author of XGBoost is Taiki Chen. Here is his quote on why he gave the algorithm the name XGBoost. The name XGBoost actually refers to the engineering goal to push the limit of computational resources for boosted tree algorithms, which is the reason why so many people use XGBoost. All right, so now that we know what it is, you might be thinking, well, that's great. I don't know what a gradient boosted decision tree is. All right, that's fine. We're going to get into the weeds of gradient boosters later. For now, I just wanted to provide you with a high-level definition and tell you why we use them. XGBoost supports many interfaces. This course will use the Python interface as well as the scikit-learn implementation. XGBoost in Python and scikit-learn's XGBoost implementations are fundamentally the same. The XGB classifier and the XGB regressor wrapper classes for XGBoost were created for use in scikit-learn. Now that we have a definition for XGBoost, the next question might be, well, great, why do we use it? Why is it so popular? We use it because it excels at two of the most widely used problems in the real world, classification problems and regression problems. Currently, most models are being sourced from relational databases. That means the data is already in a structured state. Since the data is already structured, it's easier to model. Because it's structured data, we use XGBoost on the structured datasets, and we do so because it rarely loses. If we take XGBoost models and put it head-to-head against any other model on structured datasets, the majority of the time it's going to win, which is why it's become so successful in competitive modeling and the real world. All right, in this lesson, let's walk through a demo of XGBoost, a very simple demo. Now, you may be thinking, why at this juncture would we do a demo when we haven't learned anything about it? Well, two reasons, really. Number one, I don't want you to get bored. If you get bored, that's bad. And secondly, because programming is a hands-on sport. So the only way you get good at programming is to do it. All right, so in our first cell, these things are called cells. We're going to bring in a whole bunch of modules. All right, now let's go ahead and add another cell. Instead of importing just what we need, we can import the entire library. So we could say import NumPy instead of importing load text. All right, so we could do that. However, that's not very Pythonic. We often only bring in what we need. So from these libraries here, I'm bringing in only what I need: load text, the XGB classifier, which is XGBoost, and train test split and accuracy, so we can score a model. All right, in this next cell, let's go ahead and, did I run that first cell? Run it, yep, run it again. All right, so we're loading our data set. Now, if we wanted to see what our data set looked like, we could come down here and say data set. And that's what our data set looks like. Lots of numbers, which is what we want. Let's kill that. All right, now we're going to separate our data set into the training data, and we're also going to tell XGBoost, or we're going to tell our model, what the target variable is. The target variable is that thing we're trying to predict. So let's go ahead and run it. Now, let me show you what I mean for that. Let's open up. Let's hit X, X0, starting at the 0 position, and our array, go to the 8th position, and what does our data look like we're going to model? There it is. Great. So what's the target variable look like? Let's hope it's numeric 2. There we go, 1s and 0s. So if it's 1s and 0s, and this is our answer, then we have a binary classification problem. Right? So let's go ahead and kill that. Here, seed. Seed is used for reproducibility. It doesn't have to be set to 7. We could use any number we want. Test size. We're setting aside our data into 2 segments, right? The test data and the training data. And here we're just specifying the amount, the percentage, 33%, will be our test data. And here's the function we're going to use called train test split. See it? Yep. And we import it. And you can see up here, we imported it here from sklearn, sklearn and scikit-learn. All right, so you can see that we're passing in the test size and the seed into the train test split function. So let's go ahead and do that. Here, let's go ahead and actually, let's come up here. Cell. Let's clear our output. There we go. Nice and clean. So here is our model. We're creating a variable called model to hold the XGB classifier, which is XGBoost. And now we're going to fit it to Xtrain and Ytrain, right? Our training data, not our testing data yet. So let's go ahead and do that. All right, when we print our model out, we get the hyperparameters. That's what these are. These are hyperparameters that we could pass into our model. So let's say we wanted our max depth something other than 3. These are the max depth of the trees in the model, 6. We do that. We don't want anything there for now. So we're not going to pass in any hyperparameters. We're going to run that. We're creating a variable down here called ypred to hold the predictions of our test. Look, test, right? Now we're on to the testing data set. This section that we set aside. Right, we're going to round. Right, we're using round to value of the ypred. We're going to import accuracy. That's what we did up here. Remember, accuracy score. We imported that to use it because we need a metric for our model, and that metric is going to be accuracy. We're going to round it to 100%. So let's see what it looks like. The accuracy on our model is, all right, something's really wrong. That should not be 55%. What did I do wrong? All right, so let's come up here and rerun this. Yep. I missed something, didn't I? I missed the way. There we go. That's much better. 73%. And actually, that's not really good. It should be a little higher than that. All right, so we just walked through our first XGBoost model on the Pima Indian diabetes data set. All right, in this brief lesson, let's review what we covered in this section. XGBoost is a gradient booster. Gradient boosting is a machine learning technique for regression and classification problems, which produces a model in the form of an ensemble of weak predictor models, typically decision trees. There are 2 broad categories of models. There are deep learning models, and there are traditional models. XGBoost is a traditional model. Most applied machine learning is supervised learning. That means the models learn patterns in existing data sets. XGBoost is a supervised machine learning algorithm. In the applied space, the majority of problems are either classification or regression problems. XGBoost excels at both classification and regression problems. XGBoost stands for extreme gradient boosting. There are other gradient boosters. However, XGBoost has become the gold standard in competitive modeling. In this lecture, let's discuss what will be covered in this section. In this section, you'll learn all about gradient boosters, not just XGBoost, but the entire class of models and how they work. Gradient boosting is about taking a model by itself that is a weak predictive model and combining that model with other models of the same type to produce a more accurate model. The idea is to compute a sequence of simple decision trees, where each successive tree is built for the prediction residuals of the preceding tree. In gradient boosting, the weak model is called a weak learner, Weak learner and weak model are synonymous terms. In this section, you'll learn about recursive binary splitting. Recursive binary splitting is a numerical procedure where all the values are lined up at different split points and tried and tested using a cost function. Gradient boosters are ensembles. Ensemble Learning uses several machine learning models to build a more efficient learning algorithm to improve the accuracy of the prediction. With this approach, multiple weak learners, remember these are weak models, are combined to improve our model's results. The algorithms are often referred to as meta-algorithms. Meta-algorithms are models that combine several machine learning techniques into one predictive model in order to decrease the variance. In this section, you'll learn the difference between bagging and boosting. Gradient boosting is a powerful technique for building predictive models. Gradient boosting is about taking a model that by itself is a weak predictive model and combining that model with other models of the same type to produce a more accurate model. The idea is to compute a sequence of simple decision trees, where each successive tree is built for the prediction residuals of the preceding tree. In gradient boosting, the weak model is called a weak learner. The definition used when combining various machine learning models is called an ensemble. The weak learner in XGBoost is a decision tree. Therefore, we need to understand how the decision tree works before we can understand boosting. A decision tree is a graphical representation of all the possible solutions to a decision based on certain conditions. These trees can be viewed as a set of simple rules that contain simple clauses put together into a large equation. They are a series of if-then statements that segment your data into similar groups. The rules can be easily understood and can provide observations that are not always obvious with simple data inspection. It's called a decision tree because it starts with a single box or root, which then branches off into several solutions, just like a tree. While this definition is a little obtuse, several examples will help make this concept a little more lucid. Let's define a few core terms first. Let's start off with the tree. The start of the tree is called the root node. This node will split on the most important attribute in your dataset. After that initial split come the decision nodes. They are referred to as decision nodes because the split in the data has been made that has caused the tree to branch out into separate directions. Hence, an initial decision has been made on how to best split that data. The leaf node will often lead to the answer or the predicted value. Please keep in mind these examples are contrived and are only for instructional purposes. Let's take a look at one of the most famous datasets used in machine learning, the Titanic dataset. The Titanic was a British passenger liner that sank in the North Atlantic Ocean in the early morning hours of April 15th in 1912. There were approximately 2,200 people and crew aboard the ship, and more than 1,500 died, making it one of the most deadly commercial peacetime maritime disasters in modern history. One of the top reasons that the sinking resulted in such a great loss of life was that there weren't enough lifeboats. Although there was some element of luck involved in surviving the sinking, some groups were more likely to survive than others. Our picture on screen is the Titanic dataset. Our target variable, or that thing we want to predict, is called survived. Because the target variable is a 1 or a 0, this is a binary classification problem. Let's attempt to answer some questions based on our data. How would a decision tree be applied to this dataset? The very first thing the decision tree algorithm does is look for the attribute that is most important in the dataset. The phrase most important here is a little relative, and it's based on some mathematics behind the scene that we're going to skip for now. The dataset has an attribute for gender titled sex. The algorithm has decided that the single most important attribute was the sex attribute. More specifically, is the passenger male or not? The root node is split into two groups, male and female. After the first split has been completed, the algorithm continues to analyze the other attributes in the dataset. The algorithm decided that the age of the passenger was the second most important attribute in the dataset. Specifically, is the passenger older than 9.5 years of age? That answer led to the split based on another attribute in the dataset, SIB-SP. The attribute SIB-SP simply means, did a passenger have siblings aboard at the time of the sinking? With each successive division, the members of the resulting sets become more and more like each other. Creating a tree involves deciding which features to choose and what conditions to use for splitting, along with knowing when to stop. Decision trees are helpful, not only because they are visual representations that help you visualize what you're thinking, but also because the design of a decision tree requires a well-documented thought process. Decision trees help formalize the brainstorming process so that we can identify more potential solutions. Creating a binary decision tree is the process of dividing up an input space. A greedy approach is used to divide the space called recursive binary splitting. Recursive binary splitting is a numerical procedure where all the values are lined up into different split points and tried and tested using a cost function. A cost function is something we want to minimize. Let's try to define a cost function in simplest terms. Whenever you train a model on your data, you're producing some new values, the predicted values, for a specific attribute. However, that specific attribute already has some values which are the real values in the dataset. The closer the predicted values are to the corresponding real values, the better your model. You're using a cost function to measure how close the predicted values are to their corresponding real values. The split with the best cost, which is really the lowest cost we want to minimize, is selected. All input variables and all possible split points are evaluated and chosen in a greedy manner. Recall earlier the example of the tree from the Titanic dataset? The very first split occurred with the split of the root node. At this juncture, all the attributes in the dataset are considered, and the training data is divided into groups based on that split. The split that cost the least amount is chosen, which in our example is the sex of the passenger. The algorithm is recursive in nature, as the groups formed can be subdivided using the same strategy. The decision tree is a greedy algorithm. A greedy algorithm is an algorithm that is concerned with making the best decision at each step in the process. In many problems, a greedy strategy does not produce an optimal solution. For example, in our animation on screen, the greedy algorithm seeks to find the pattern with the largest sum. It does this by selecting the largest available number at each step. The greedy algorithm fails in this case to find the largest sum because it makes decisions based on only the information at one step, without regard to the overall problem. With the goal of reaching the largest sum at each step, the greedy algorithm will choose what appears to be the optimal immediate choice. So it chooses 12 instead of 3 at the second step. And that's not the best solution to our problem, if we're trying to reach 99. The complexity of decision tree is defined by the number of splits in a decision tree. Simpler trees are preferred. They are easy to understand and less likely to overfit your data. The question now becomes, how do you know when to stop growing your trees? The more attributes you have, the more splits, the larger the tree. You need a mechanism to stop the growth to prevent the tree from overfitting. One way of doing this is to set the maximum depth of your trees for each iteration. For example, in XGBoost, you can limit the depth of your trees in your model by passing in the max depth parameter. In our contrived example, the maximum depth of any given tree is 2 layers. The deeper the tree, the more complex the model, the more likely it is to overfit. The performance of a decision tree can be further enhanced through pruning. Pruning involves removing the branches that make use of features having low importance. Using this approach, we reduce the complexity of the tree, thus increasing its predictive power by reducing overfitting. By pruning, we mean that the lower ends, the leaves of the tree, are snipped until it's much smaller. These leaf nodes are removed only if it results in a drop in the overall cost function on the entire dataset. Hello everyone, welcome back. Let's go ahead and use XGBoost and label and code some values or a value. So the first thing we want to do is bring in XGBoost and we want to give it an alias. One of the nice things about scikit-learn here, sklearn is scikit-learn recall, is that it has data sets we can import into our environment and not have to pull others in. Like we can just use theirs without having to go search it down from wherever it's located. Here we're going to use train test split. We've seen this before. We're going to use this to separate our data into disparate training and testing sets. Label encoder, we're going to encode a label. All label encoding really is taking textual data and making it numeric. All right, here we're importing XGBoost again. I'm not sure why I did that. Metrics, we've seen this before. We need accuracy. We need to score our model. So we'll use the metrics module from within scikit-learn and use accuracy to gauge the score of our model. Here, we said we're going to use scikit-learn to load the dataset, the iris dataset. Here we're creating a variable. We're going to load the iris dataset. Let's go ahead and run this. Let's go ahead and load our dataset. All right, let's go ahead and separate the X and Y variables out. Here's the data. We're telling our model, this is the data we want to train on, and we want to test on also. But firstly, we want to train on it. And here's our target variable. Here we're using train test split to separate our data. Here we're just passing in the variables. Recall the last time we created variables and then we passed the variables in. Here we're actually setting those variables. We're still passing in the variables, but we're hard coding the variables into train test split. Just two ways you could do it. Here the 20% says 20% for our training data set, random state for reproducibility. So let's go ahead and execute that. X is not defined. Sure it is. Is it a small x though? Let's find out. Or is it a large x? Sure, x is defined. I just defined it. Don't tell me it's not defined. Oh, it's telling me. X and y. Did I not run that? Talk about quirky. Maybe I typed it in wrongly both times. That doesn't matter. It worked this time. All right, so here we have our data, right? This is our data. It looks good. That's our training data and our testing data. Over here we have this, iris setosa. This is our target variable. And this is bad news for us because it's textual and we won't be able to use it. So what we do is we change this label. We encode this label using label encoder to make it numeric. All right. So to do that, we create a variable called label encoder, and we say label encoder because this is the function. Label encoder, we're fitting it to y. Why y? Well, because y is our target variable, right? We don't need to fit it to any of the data. All this data is correct. We need to fit it to the target variable, which is this. We need this numeric. All right, so that's why we're transforming it. We're fitting into y, and with the label encoder, you fit transform. So you take these two steps. You fit, and then you transform it. All right. Y is not defined. Holy cow. Let's copy it because it surely didn't like. Y is defined. Don't tell me it's not defined. Python. And that's what we want to see. We've gone from this, right, to this. Each one of these now is a 1 or a 0, all right? Down here, let's move on to defining our model. No hyperparameters. We're just going to use the XGBoost classifier. We're going to train and test. We're going to fit it on our training data. X, Y, and Y training. All right, train, not testing here. Nice. Let's go ahead and print out some predictions. Now we've moved from testing. Right, we're going to test now on this data. This is that 20% we withheld, right up here. We withheld that data so we can train on it. This is data it hasn't seen yet. It's seen the 80%. All right, let's go ahead and do that. What do we have here? Deprecated warning. Great, thanks. We can ignore these as a general rule. And let's go ahead and run this. And that's not bad. So XGBoost was able to predict to the tune of 90% accuracy on this model. Now that we have a high-level understanding of how decision trees operate, let's learn how they're combined in order to make a more accurate model. Ensemble Learning uses several machine learning models to build a more efficient learning algorithm to improve the accuracy of the prediction. With this approach, multiple weak learners are combined to improve our model's results. Rather than just relying on one decision tree and hoping we made the right decision in each split, ensemble methods allow you to take a group of decision trees into account, calculate which features to use at each split, and then use the final predictor to make an aggregated result of the sampled decision trees. In supervised machine learning, regardless of the approach you choose, classification or regression problems, the choice of the model is extremely important to have any chance of obtaining the best results. For the model, we want the model to have low bias and low variance, but that's very difficult to achieve. Therefore, we identify a point where the difference between the bias and variance is low. Let's define these terms. When we train a model on training data, the error between the predicted value and the actual value is bias. Bias refers to error due to oversimplistic assumptions or faulty assumptions of the algorithm. Bias results in underfitting of the data. A high bias means our learning algorithm is missing important trends among the features. Variance is the opposite of bias. Variance refers to the error due to overcomplex solutions. This happens when the model tries to fit the training data as closely as possible. With high variance, the model's predicted values are extremely close to the actual values from the training dataset. The algorithm copies the training data's trends, and this results in loss of generalization. High variance gives rise to overfitting. In machine learning terminology, underfitting means the model is too general, leading to high bias, while overfitting means the model is too specific, leading to high variance. When training a model, it's important to have a balance between these two. Since you can't realistically avoid bias and variance altogether, this is called the bias-variance trade-off. With Ensemble Learning, we assemble groups of weak learners. These weak learners are models that can be used as the building blocks for designing more complex models. The weak learner in XGBoost is a decision tree. These base models, or these weak learners, don't perform as well by themselves, either because they have a high bias or because they have too much variance. In order to achieve a bias-variance trade-off, the weak learners are combined to create ensembles that achieve better performance. Most of the time we use a homogeneous base learner. That simply means we use the same model to create the ensemble. And in our case, and in most of the case of gradient boosters, we use decision trees. The algorithms are often referred to as meta-algorithms. Meta-algorithms are models that combine several machine learning techniques into one predictive model in order to decrease the variance or bias. All right, in this lesson, let's talk about bagging and boosting. Bagging is used when you want to reduce variance. The idea is to create several subsets of data from training samples chosen randomly. Each collection of a subset of data is used to train the decision trees. As a result, we end up with an ensemble of different models. When bagging with decision trees, we are less concerned about the individual trees overfitting the training data. The individual decision trees can grow deeply. The trees are not pruned. These trees will have both high variance and low bias. In our example, several base models execute different bootstrap samples and build an ensemble model that averages the results of the weak learners. Boosting is another ensemble technique used to create a collection of models. In this technique, models are learned sequentially, with early models fitting simple models to the data, and then analyzing the data for errors. Recall that with bagging, we had to run each model independently, and then aggregate the outputs at the end without any preference to the model. In other words, with boosting, we fit consecutive trees at every step. The goal is to solve the net error from the prior tree. Unlike bagging, boosting is all about teamwork. With each decision tree, the weak learner dictates what features the model will focus on next. When an input is misclassified, its weight is increased, so the next decision is more likely to classify it correctly. In our example, in our case a decision tree, is trained on a dataset. On the model's first iteration, the weak learner makes a prediction. However, its accuracy isn't that good. Recall that's the very definition of a weak learner. Once the first iteration is completed on the training dataset, it's updated based on the previous results. In the Titanic dataset, the root node was split on sex. More specifically, was the passenger male or not? If we were using a booster, that split might have produced a shallow tree. These shallow trees are often referred to as decision stumps. Gradient boosting is a machine learning technique for regression and classification problems, which produces a model in the form of an ensemble of weak predictive models, typically decision trees. It builds the models in a stage-wise fashion, like all other boosting methods do, and generalizes them by allowing optimization of arbitrary differential loss functions. Gradient boosting involves three core steps. The first step that is required is that a loss function be optimized. That loss function must be differentiable. A loss function measures how well a machine learning model fits the data of a certain phenomenon. Different loss functions can be used for speech or image recognition. The second step in gradient boosting is to use a weak learner. In gradient boosting, the weak learner is a decision tree. Specifically, regression trees are used to output the real values for the splits, and whose output can be added together, allowing subsequent models' outputs to be added to the correct residuals in the predictions of the previous iteration. The third step is combining many weak learners in an additive fashion. Decision trees are added one at a time. A gradient descent procedure is used to minimize the loss when adding trees. That's the gradient part of the gradient boosters. Gradient descent optimization in the machine learning world is typically used to find parameters associated with a single model that optimizes some loss function. Gradient boosters are meta models consisting of multiple weak learners whose output is added together to get an overall prediction. The gradient descent optimization occurs on the output of the model and not the parameters of the weak models. Let's take a look at this process pictorially. In our example, you can see that gradient boosting adds these submodels incrementally to minimize the loss function. Earlier, we said that gradient boosting involved three main steps. In our example, the weak learner being used as a decision tree. Secondly, the trees are added sequentially. And lastly, with more iterations, the error of the model is being reduced. Hello everyone, welcome back. In this example, we're going to work through a demonstration that we've already worked through. However, this time, instead of train test split, we're going to use the gold standard in separating our data or segmenting our data called KFold Crossvalidation. In our first cell, we're going to import some things we need. From NumPy, we're going to import load text, XGBoost, XGB classifier. And from scikit-learn, model selection, under model selection, we're going to do cross-val scores so we can see the score of each of the folds, and stratified KFold. And this is simply a way to segment your data so that the entire data set is tested. And I'll explain that in a second. So did I run this yet? Let's go ahead and run this. Here under import warnings, I'm going to show you how to depress those deprecated warning messages. All right, I'll show you that in a second. All right, in cell 2, let's go ahead and create a variable called dataset. And let's load the Pima Indian diabetes dataset. We don't need to look at the dataset. We know what that looks like. We do need to separate it into training and testing, and then tell it what the target variable is going to be. So let's go ahead and do that. In our next cell, we want to use XGBoost, so we're going to create a variable called model to hold that. And here, you can see we're going to ignore the filter warnings. All right, so let's go ahead and ignore any filter warnings. All right, here we're creating a variable KFold to segment our data into 10 different splits. Here it says the splits are 10. It doesn't have to be 10. It can be anything you like. However, 10 seems to be a number that's often used to segment your data using KFolds. So that's what we'll go with for now. So we're passing in that, and we're passing in random state, again, for reproducibility. So we can run this model time after time and get the same results. All right, here we've got the results under the variable to hold the results. And we're going to print it out so we can see the result of each score of each fold, so to speak. So let's go ahead and, did I run the ignore warnings? I think I did. I keep forgetting if I ran the previous cell. Let's go ahead and run this. And as you can see, this is the score, right, for each fold. So there, we split the data into 10 different folds. So it tested 10 different splits. So I'm hoping 1, 2, 3, 4, 5, 6. There are, I just decided to count that to make sure it wasn't going to make a liar out of me, to see that we have 10 different scores. All right. Here we're going to print the accuracy of our model now. 76%. Yeah, it's all right. And the score is not important. What's important now is that you understand how to use KFold validation with XGBoost models. Let's summarize what was covered in this section. In this section, you learned the difference between bagging and boosting. With bagging, the idea is to create several subsets of data from training samples chosen randomly. Each collection of a subset of data is used to train the decision trees. With boosting, you fit consecutive trees at every step. The goal is to solve the net error from the prior tree. Unlike bagging, boosting is all about teamwork. In this section, you learned about the decision tree. In most boosting models, the decision tree is the weak learner of choice. A weak learner is a model whose performance is a little better than guessing. With these weak learners, you want the tree depth to be shallow to avoid overfitting. In this section, a loss function was defined. A loss function is a measure of how well the machine learning model fits the data of a certain phenomenon. Different loss functions may be used depending on the type of problem. Greedy algorithms were discussed. A greedy algorithm makes the best decision at every step in the process without regard to the entire problem. Gradient boosters like XGBoost are greedy algorithms. In this section, the 3 core steps in gradient boosting were covered. The first step is the loss function must be optimized. The second step is to use a weak learner. In most gradient boosters and XGBoost, that weak learner is a decision tree. The third and final step is combining many weak learners in an additive fashion. In this section, ensemble models were defined. Ensemble Learning uses several machine learning models to build a more efficient learning algorithm to improve the accuracy of the prediction. With this approach, multiple weak learners are combined to improve our results. In this lecture, let's cover what you'll learn in this section. If you took a quick perusal of the lessons, one thing would jump out. Almost every single lesson in this section is a demo. In this section, you'll learn a lot of things you can do with XGBoost from a code perspective. Very little of it will be theory. XGBoost and many other models can handle empty values. However, it's been my experience they don't handle them very well. In this section, you'll get to see the results of how XGBoost handles missing values and why it's not a good idea to let the model do that work. In this section, you'll learn how to save or serialize your models to disk. Once your XGBoost model is ready to go live, you'll need to save it and recall it from disk. In this section, you'll learn about importance scores, what they are, how to use them, and why it's probably not a good idea to rely on them too heavily. In this section, you'll learn what early stopping is and how to use it. It's not the most intuitive tool, but it might save you some processor cycles on those larger builds. In the course, we've seen a lot of classification demos, which is good because a lot of applied machine learning is classification. However, XGBoost also excels at regression models. So in this section, you're going to work through a regression model. In this section, you'll learn about the default hyperparameters suggested by XGBoost and scikit-learn. All right, there's a lot of code in this section, so let's get started. All right, everyone, welcome back. In this one, we're going to take a look at immutation. Immutation, this word up here, is a fancy word that means replace. And that's all it means. We're going to replace some values. This is going to be a really interesting one because it's going to show just how important data cleansing is. Let me tell you a story. I was on a call on a project with some people from Microsoft, and I was working on a course for them. And they said, with XGBoost and even with some of their models, their gradient booster is called LightGBM, the model can handle empty values, so we don't have to worry about that. Well, I'm going to show you why you have to worry about that. In this first cell, we're going to import what we need. We're going to use pandas. We're going to use model selection. We're going to use XGBoost. So let's go ahead and import those. Let's go ahead and read the Titanic CSV in. These are the columns that I want. So let's go ahead and specify those columns from that data set. All right, let's take a look at the top 5. Do we have any? We don't have any NaN values. All right, so let's go ahead and find some NaNs. All right, so in the age column, we have some NaN values. All right, first, let's get rid of this text. So sex, it says male and female. We need to get rid of that. So we're going to map males to 0 and females to 1. Let's go ahead and look at the top 25 to see that we accomplished that. And we did. Good. And our age still has the NaN values, right? NaN in Python is not a number. So let's see how well XGBoost handles those NaN values. All right, so let's skip down to specifying the X and Y variables. So survived is our data, and survived is also our target variable. Let's go ahead and split it using train test split. Let's go ahead and define our model. Great, we've seen this before. We're probably getting used to this by now. Let's go ahead and create some predictions. And let's go ahead and take a look at the results. So 78% accuracy. All right, well, that's a good score. Let's come up here and do this all over again. All right, so I'm going to reload the data file. I want to take a look at the attributes or columns I need. All right, here we go. I need to remap the sex column to male and females. let's take a look at the head function so we can see. Yep, okay, we're in good shape. All right, now what we're going to do is do something called mean value immutation. All right, and again, more fancy words. And mean value immutation is just a fancy word that means we're going to replace the NaN values, our empty values, with the mean. So let's go ahead and do that. All right, and again, we're going to step through the exact same process. We're not going to change anything. All right, a little less accuracy than the last one, but not much of a big deal. All right, let's move on. Now let's try something else. Let's do the whole process over again. Let's clean this here. It's cells. Let's go to all outputs. Clear. All right, now we don't have to import, but let's go ahead and bring in our Titanic data set clean again. Let's go ahead and specify only the attributes we need. Let's take a look at the head function. Great. Let's go ahead and map our columns again. Great. The head. Okay, great. Looking good. Now, what we're going to do is drop all the NaN values from the data set. So all these, we're just dropping them. And any other NaNs and any other attributes or columns are going. All right. We want them gone. All right, so we don't have to do the mean value immutation step again. Let's go and walk through the model again. Yikes. A little different, huh? Quite a bit of difference in the accuracy when you use only the raw data. All right, so this is the reason you clean your own data. That's the reason that you don't let the algorithm, no matter what that algorithm is, handle empty values. I'm sure you've heard the axiom, your model is only as good as the cleanliness of your data. And if you didn't hear that, well, you heard it from me. So make sure you clean your data yourself. Don't rely on any algorithms to do the immutation for you. Hello, everyone, and welcome back. In this lesson, we're going to talk about Pickle. See, Pickle is the name of our lesson. And, oh, sorry, I didn't mean to do that. Let's cancel Pickle. Pickle is the name of a library in Python used to serialize your models to disk. Serialize is a term that simply means save to disk. So let's go ahead and work through our model again. Yes, head functions. Yeah, okay. Let's go ahead and drop all, because that was the best result. Let's go ahead and map. Yep, good, good. Okay. And there is our accuracy. All right, so we've gotten to this point. Our model is 83%, and we're going to say that this is our production-ready model. Now, 83% is really good, but it probably can be tweaked a little further. However, for our purposes, 83% is great. We're going to save this model and use it in production. So the first thing we're going to do is import Pickle. After that, we're going to use the dump function from within Pickle to save it to disk. And I'm going to call it pima.pickle.dat. And we're going to print out saved our model to disk. Now, if we navigate to the location where our notebooks are saved, let's hit date modified, you can see that our model has indeed been saved to disk. All right. So sometime later, we want to recall that model from disk. We want to call it. All right, so we're going to create a variable called load model. We're going to use the load function, and we're going to open that file that's been persisted or saved to disk. Great. All right, let's create a variable called ypred, and now we're going to hold the contents of that pickle.dat file and train it against xtest, all right, against our testing data. So our results should be identical, or really close. Yep, we can ignore that. And let's see the accuracy of this model, the one that was saved to disk and run later. And it is indeed the exact same. Now, one little caveat about Pickle is specific to Python. And that's how we save or persist our XGBoost models to disk. Hello and welcome back. In this lecture, let's go ahead and plot the importance of each attribute. All right, so in XGBoost, we have this tool, this function called plot importance. And it's going to give us the importance of each of our attributes or our columns in the data set. All right, pretty straightforward. Not only that, we're going to import matplotlib. Well, actually, we're going to import plyplot from matplotlib. And we're going to create a graph that's going to show us the importance of each attribute. And it really is 4 lines of code, right? This is our model, right? We've already defined that up here. And our model is XGBoost. And if we run that, it tells us that age is by far the most important. Recall that features and attributes and columns, they're all synonymous terms. So these are columns in the data set. Age is the most important. P-class the second. SibSP, it looks like, is really close with sex. And then we have parch, which is parent and children, right? So with 4 lines of code, we can plot the importance of each attribute in our data set. That's a pretty cool feature. Hello and welcome back. So as we look at our feature importance scores, how do we use them? Well, we can see, according to XGBoost, that age is number 1, P-class is number 2, SibSP is number 3. Why do we need sex and parch? Isn't the idea that less is more in machine learning? Can't we just use age, P-class, and SibSP to build our model? Sure, let's go ahead and do that. So let's just use age, P-class, and SibSP. Let's go ahead and import our Titanic dataset clean. Let's move down. This is the one we did prior. Let's move down and create a variable called data to hold just P-class, age, and SibSP, and of course our target variable. Let's run that. All right, that looks good. We don't have to map sex since sex is no longer in our data set. So let's go ahead and do the drop all on that. Let's go ahead and continue to build away, telling that sex is indeed our target variable and we want to drop it. All right, let's go ahead and split it up. XGBoost is our classifier. Great. Let's go ahead and look at our predictions and let's see how we did. All right, so something's a little off. 75%. That's a little less than what we had before at our 80 whatever percent that was. So can we use age, P-class, and SibSP? Is sex really that low in the totem pole? Well, let's go load sex back up into our data set and see what happens. Let's go ahead and let's go ahead and clear our output. And we're going to load sex. We can just copy this, can't we? Back up. So we need to import our data set again. And now we're going to add sex. And now we're going to look at the head to see if we definitely have everything we need. Yep. And we need to change this, right? This is textual. This needs to go to numbers. So we need to do our mapping now. Let's take a look. All right, lots of numbers. Oh, we've got nans. We got to get rid of those nans. So let's kill those nans. All right, nans are gone. Now let's continue just to walk through the model again. Huh. 85%, which is our best score on this so far. So the importance of our sex attribute certainly can't be that low if the accuracy of our model varies that much. Let's see if we indeed, it does say that sex is indeed low again on the totem pole. Doesn't make a lot of sense. So we've restricted it from 4 variables, and we have our best model after including the sex attribute. So what have we learned by doing this exercise? Well, we've learned that you've got to take these feature importance scores lightly, all right? You are going to have to do your own analysis, and that's why you test various scenarios. So we were able to get our best model, our best score so far, by using 4 attributes instead of 3. And the sex attribute, as it turns out, was very important and probably isn't really the 4th most important attribute in our data set. Hello and welcome back. An XGBoost model can evaluate and report on the performance of a test set for the model during training. It supports this capability by specifying both the test dataset and evaluation metric on the model fit function when training the model and specifying verbose output. XGBoost supports a suite of evaluation metrics for classification error. All right, let's take a look at how this is accomplished. All right, so here it is on the fit function, xtrain, ytrain. Our evaluation metric is error, verbose to true. Now let's check out our results. Hopefully our error will start high and then decrease. So it is. We're moving down, down, down. So the default number of iterations on an XGBoost model is 100, as you will see in a second. So it looks like as we move towards the bottom, towards 100, we have indeed reached the lowest error point, which is 14,521. Now the bad news is it stops at the 100th iteration. So what if we want to see some iterations beyond that? Well, we can specify that by passing in n estimators to our model. So let's go back up and we'll pass in n estimators to see if we can see beyond that 100th iteration and if the error continues to reduce. Go back and look beyond that, 14,521. No, as a matter of fact, we see a jump here and it looks like around the 100th, well, it looks like actually much earlier than that, 14,521. Looks like pretty early, actually. So here in this iteration and moving forward, it looks like the error rate stabilizes and it's the lowest point. So indeed, after 100 iterations, it looks like our error is the lowest it will be. And that means we can come up and come up here, and remove that. Because with our default, we have seen the lowest error rate. Right? And then we could walk this through to the end. Let's run this again. Let's move this back down. Test and see what our accuracy is. Yep, same as last time, right? All right, in this lesson, we've seen how we can monitor our model's performance and go ahead and pick out the lowest error for a given iteration of our model. Hello and welcome back. You can retrieve the performance of a model on a evaluation dataset and then plot it to get insight into how learning unfolded while training. This process is called evaluating with learning curves. You provide an array of x and y pairs to the evaluation metric argument when fitting the XGBoost model. In addition to the test set, you also provide a training data set. This will provide you with a report on how well the model is performing on both training and testing datasets during training. Additionally, the performance of a model on each evaluation set is stored and made available by the model after training by calling the model eval's result function. This returns a dictionary of evaluation datasets and scores. Each of the validation 0 and validation 1 correspond to the order that the datasets were provided to the eval set argument when you call the fit function. A specific array of results, such as for the first dataset and the error metric, can be accessed. Additionally, you can specify more evaluation metrics to evaluate and collect by providing an array of metrics to the eval metric argument of the fit function. You can then use these collected performance measures to create a line plot and gain further insight into how the model behaved on the training and the testing datasets over the training epochs. In our example, two plots were created. The first shows the logarithmic loss of the XGBoost model for each epoch on the training and the testing datasets. The second plot shows the classification error for the XGBoost model for each epoch on the training and the testing sets. When we take a look at the log loss plot, it looks like there's an opportunity to stop learning early, perhaps somewhere around epoch 20 to epoch 40-ish. You can see a similar story for classification error, where the error appears to climb back up around epoch 40. Hello and welcome back. XGBoost supports early stopping after a fixed number of iterations. In addition to specifying a metric and a test dataset for evaluation of each epoch, you must specify a window of the number of epochs over which no improvement is observed. This is specified in the early stopping rounds parameter. Now the word I'm using here is epoch, and it's spelled E-P-O-C-H. The number of epochs is a hyperparameter that defines the number of times that the learning algorithm will work through the entire training dataset. All right, so we specify the early stopping rounds in our fit function. As you can see, here is our fit function, and here is early stopping rounds. Now, it's a little confusing because, at least in my head, you would think that, okay, it's going to run 10 iterations and it's going to stop. Well, that's not really how it works. It runs until it finds the least error within a certain number of rounds, as close as it can to the 10 that you specified. That in itself is a little strange. So here we go. So we can see that the best one was 16, whatever that is, at number 7. All right, so it found the best iteration as close as it could to 10, which was number 7. So why did it run after 7 then? I don't know. Now, I don't use early stopping rounds because it is very buggy. However, it is a parameter in XGBoost that I wanted to show you for full disclosure. And if you want to use it and you have success using it, well, there it is. Hello and welcome back. So far, we've focused mostly on classification models. However, recall that XGBoost excels at building classification and regression problems, the two most common types of models in the applied space. So let's go ahead and build a regression model. Let's evaluate home prices collected from the suburbs of Boston, Massachusetts. This was a Kaggle competition. Now the competition's over. However, a great score can still be a resume bullet point. All right, like always, let's import the libraries we need. You'll have to do this in the first cell, but you can do it wherever you like, just as long as you bring them in before you use them. All right, a good thing about this data set is that it is included in scikit-learn. Now, there are a lot of steps in the code, so I've had comments to make it easier to understand. In the first line of code, we're creating a variable called Boston and loading the data set into that variable. In the next line of code, we are setting our data set to a pandas data frame. In the third line of code, we are assigning the columns to feature names from the dataset scikit-learn. In the fourth line of code, we are assigning the attributes price to our target variable. Next, we are assigning X to training data and Y to the target variable. In the last line of code, we're using a new object. This is from XGBoost and it's called a D-matrix. A D-matrix is an internal data structure that's used by XGBoost that's optimized for both memory efficiency and training speed. All right, the next thing we want to do is separate our data. We've passed in the parameters to our test size to create an 80-20 training testing split. Additionally, we're passing in and setting random state parameter to 9 for reproducibility. In the next line of code, we're going to create a variable called XGBREG and assign that variable to our regressor model in XGBoost. We're passing in the type of model we're building. Take note, this is an XGBoost model, not a scikit-learn classifier. On the second line of code, we are fitting our training data to our model. Lastly, we're creating a variable called preds to hold the results of modeling our testing data. Now that our model has been trained and tested, it's time for some results. We've created a variable called RMSE to house the calculation, which is the root mean squared error on our test data. The final code prints out the results of our prediction, and that score is actually really good. It's actually a stellar score on this data set, providing you with yet another resume bullet point. So in the course, we've shown mostly classification because most everything you're going to do in the real world is classification, but also there's going to be a lot of regression problems. And we've just showed you an example of a regression problem. Parallelism and gradient boosting can be implemented in the construction of individual trees, rather than in creating trees in parallel like a random forest. Recall that in boosting, trees are added to the model sequentially. The speed of XGBoost is both in adding parallelism in the construction of the individual trees and in the efficient preparation of the input data to aid in the speed up in the construction of the trees. The term parallelism refers to the technique to make programs faster by performing several computations at the same time. This requires hardware with multiple processors. The XGBoost classifier and the XGBoost regressor wrapper classes for XGBoost for scikit-learn provide an in-thread parameter to specify the number of threads that XGBoost can use during training. By default, this parameter is set to -1 to make use of all the cores in your system. Now, the majority of the time, you'll get multi-threading support for your XGBoost installation without any effort. You can confirm that XGBoost multi-threading support is working by building several different XGBoost models. by specifying the number of threads and timing of how long it takes to build each model. The trend will show you two things: that multi-threading support is enabled, and an indication of the effect it has when building models. All right, let's take a look at our notebook. In our example, we're going to use the auto dataset. It's a large toy dataset, and it'll give your laptop a workout. In the fifth cell, you're creating a list to hold the number of iterations for the example. Next, a for loop is being used to test the execution speed of the model based on the number of threads. Two different results are being printed out: the speed of the build for each iteration and a plot to show how the speed of the model decreases as the number of threads increases. The bigger the box, the faster the build. Now, if you don't see any improvement here when you're running the builds for each thread, you might need to investigate how to enable multi-threading support in XGBoost on your build. All right, hello and welcome back. In this lecture, let's talk about hyperparameter tuning, a big word that means passing in parameters into your model to enhance the performance of the model. That's all that is. And it's always an interview question. What's hyperparameter tuning? Passing parameters into a model to enhance the performance. That's it. So down here in this lesson, I've included scikit-learn's baseline recommendations and XGBoost's baseline recommendations. Now, I love scikit-learn's recommendations because it happens to be the default. Let's see, go ahead and take a look. If we print out when we run this model, it prints out the default parameters, right? So if you look at that, it's identical, which is kind of comical. All right, so hyperparameter is something we pass in here into the model, right? So let's take a look at what's ETA. The learning rate on this hyperparameter is 0.3 per XGBoost. So let's see, what was our result here? Let's see if we can get a better result. What didn't like? Predictions not defined. Let's go ahead and run. So let's go ahead and run all these. Run all below. 8380. All right, so let's remember that. I'm not going to remember that, so let's cut and paste that. Cool. Moving on. So what does XGBoost say? XGBoost says a learning rate of 0.3. So let's go ahead and find that hyperparameter. I don't know why they call it a hyperparameter. Why not just parameters? And that's what we call them in other programming languages. All right, let's go ahead and find the learning rate, which is right here. Copy, paste our hyperparameter learning rate, and they said it's going to be 0.3. So we'll create it as a 0.3. What else? Max depth. I can't say it. Max depth. It's like I'm drunk. Max depth to 3. All right. Let's go ahead and pass in the 6 that XGBoost recommends. Now let's go ahead and give this a run to see if the default now everything else is the same. Now if you look at this subsample, sample is 1, so that's why I left that one there. So if we run this, let's see if that boosts our model's performance. Nope, didn't do anything to the default parameters. So passing in XGBoost's, I can't say that today, passing in the recommendations from XGBoost doesn't really give us any performance. Now, all right, so now you know what the recommendations are, but the recommendations for scikit-learn are the default parameters, and the recommendations for XGBoost, the baseline recommendations, don't really enhance our model. Well, at least this model. Hyperparameter tuning takes a little work on your part in order to squeeze out the model's performance. Gradient boosting involves the creation and addition of decision trees sequentially, each attempting to correct the mistakes of the learners that came before it. This raises a question. So how many trees, or weak learners or estimators, is needed to configure your gradient boosting model? And how big should each tree be? Most implementations of gradient boosting are configured by default with a relatively small number of trees. The general reason is that most problems, adding more trees beyond the limit does not improve the performance of the model. The reason for this is in the way that the boosted tree model is constructed, sequentially, where each new tree attempts to model and correct the errors made from the previous sequence of trees. Quickly, a model reaches the point of diminishing returns. Let's go ahead and demonstrate this on a very large data set. The number of trees, or rounds, in an XGBoost model is specified to the XGB classifier or XGB regressor. The XGB classifier is for classification models, and obviously the XGB regressor is for regression models. All right, so I kind of broke that up for a second. So the number of trees and rounds in an XGBoost model is specified using the nestimators argument. The default for XGBoost is 100. Using scikit-learn, you can perform a grid search of the nestimators model parameter, evaluating a series of values from whatever you want. Ours are from 50 to 350 with a step size of 50. Let's take a look at the code and see what work it's doing. In our first line of code, the model is being defined. In the second line, a variable is being created to hold the iterations. Next up, a variable is being declared to hold the estimators in a dictionary. A variable KFold is created to segment the data. In the next line, a variable called grid search is being used to hold the grid search for a model. And lastly, a variable grid result is created to fit the model to the dataset. Warning, this step's pretty CPU intensive, and I have a pretty big box, and it took a while. So if you're going to test this, just, be warned. In our example, on our dataset, we're using 10-fold cross-validation, requiring 60 models to be trained. The cross-validation log scores are negative. Now that's because scikit-learn's cross-validation framework is inverted. The reason is that internally, the framework requires that all metrics that are being optimized are to be maximized, where log loss is a minimization metric. Now it can be easily made a maximizing one by inverting the scores. Now let's check out our results. So the best number for us was the nestimators equals 250, resulting in a log loss of whatever that small number is. But that's not really much better than nestimators equals 200. Either way, this approach allows you, again, a little CPU intensive or resource intensive, but this allows you to test the estimators on a given model. Gradient boosting is a greedy procedure. New decision trees are added to the model to correct the residual error of the existing model. Each decision tree is created in a greedy search procedure to select split points that best minimize an objective function. This can result in trees that use the same attributes and even the same split points again and again. The construction of decision trees in gradient boosting is a variation called stochastic gradient boosting. It's a common technique to use an aggressive subsample of the training data, the 40 to 80% range. Row sampling involves selecting a random sample of the training data set without replacement. Row sampling can be specified in the scikit-learn wrapper of the XGBoost class using the subsample parameter. The default is 1.0, which means no subsampling at all. You can use the grid search capability built into scikit-learn to evaluate the effect of the different subsamples from 0.1 to 1.0. Again, you're going to use the auto dataset. It's a nice sized toy dataset to work with. Running the examples prints out the best configuration as well as the log loss for each tested configuration. You could see the best test results achieved were a 0.4, or training trees using 40% sample of the training dataset. You can plot these mean and standard deviation log loss values to get a better understanding of how the performance varies with different subsample values. You can indeed see that 40% has the best mean performance, but you can also see, as that ratio increases, the variance in performance grows quite markedly. Now, it's interesting to note that the mean performance of all subsample values outperforms the mean performance without subsampling. In this lesson, we're going to talk about configuring the learning rate. It's important to find a good value for the learning rate for your model on a training dataset. The learning rate may be, in fact, the most important hyperparameter to configure in your model. In fact, if there are resources to tune hyperparameters, much of this time should be dedicated to tuning the learning rate. Unfortunately, you can't calculate the optimal learning rate for a given model on a given dataset analytically. Instead, you have to find a good or good enough learning rate via trial and error. The learning rate is going to interact with many other aspects of the optimization process, and these interactions may be nonlinear. Nevertheless, in general, smaller learning rates will require more training epochs. On the other side of the coin, larger training rates will require fewer training epochs. Additionally, smaller batch sizes are better suited for smaller learning rates given the noisy estimate of the error gradient. A traditional default for a learning rate is 0.1 or 0.01, and this may be a good starting point for many of your problems. Diagnostic plots can be used to investigate how the learning rate impacts the rate of learning and the learning dynamics of the model. One example is to create a line plot of the loss over the training epochs during training. The line plot can show many properties. A few examples are the rate of the learning over the training epochs, such as fast or slow, whether the model is learned too quickly, sharp rise and a plateau, or the model is learning too slowly, little or no change. Thirdly, whether the learning rate may be too large via oscillations in the loss. Configuring the learning rate is challenging and time-consuming. An alternative approach might be to perform a sensitivity analysis of the learning rate for a chosen model. This is also called grid search. This can help both highlight an order of magnitude where the good learning rates may reside, as well as describe the relationship between the learning rate and the performance. When plotted, the results of a sensitivity analysis are often U-shaped. Where the loss decreases, performance improves, as the learning rate is decreased with a fixed number of training epochs, to the point where the loss sharply increases because the model fails to converge. Hello everyone and welcome back. In this lesson, let's go ahead and create a resume worthy bullet point. Let's go ahead and create a high score on the Titanic dataset. All right, so here's my notebook. If you don't want these annotated markdown sections, just go ahead and cut them out. To me, these annotations kind of get in the way. It's like you have to hunt down the code. But I did want to include them for you if you wanted them. So in this, I did want to show you something else also. Let's go ahead and take a look at the Titanic competition leaderboard. So here is the Titanic competition on Kaggle. And if we click on the leaderboard, what do we see? We see we have a lot of people with a score of 1.0. You know what we call these people? Cheaters. There's no such thing as a model that's 100% accurate. What they do is they either overfit the model or they actually will go in and alter, kind of doctor the results. Like you upload the results in terms of the accuracy ratings and they'll actually doctor results and upload them. All right. So now for you and I, the leaderboard really doesn't matter. We're not trying to win. The competition's over. We're trying to create a resume worthy bullet point. And to do that, we need to score above 80%, and we're going to score nicely above 80% with this model. All right, so let's go ahead and walk through it. So we're going to bring in pandas. We're going to bring in train test split, and we're going to bring in our model of the hour, XGBoost. So let's go ahead and do that. Moving down to the code, we are going to bring in the Titanic CSV. Again, you've seen this quite a few times in this course. It will be included in the downloads. So let's go ahead and import it. There we go. Great. All right. We've got a data dictionary if you want. Again, if not, go ahead and just delete this. These are the columns or the attributes, if you will, in the data set. All right, let's go ahead, take a look at we're bringing in matplotlib and we're bringing in seaborn, and we're going to take a look at those that survived against those that didn't. If you don't know the history of this, it's not a happy one. I hate when this does. That's kind of like a bug. All right, so we just have to run the cell again to paint the graph. There we go. It's kind of a lopsided graph, isn't it? Either way, we can see that, yeah, wasn't very pretty. All right, so it's really an ugly cell, isn't it? Let's move down. So 38% of the total survived. That's pretty low. All right, let's take a look at one more chart. Some more exploratory data analysis, and we want to see males against females. What's that chart look like? So it looks like a lot more females survived, and if you were a male, the chances weren't too good at all. All right. We've seen this. We're going to create a variable called data to hold only the attributes we want. Great. Let's take a look at the top 50 rows. All right. Again, nothing. You've seen this already. Let's go ahead and label and code sex. Let's go ahead and take a look at the nulls. All right. So it looks like we've got quite a few in the sex column. We'll get rid of those. All right. So what I'm doing here that I haven't done before is I'm issuing drop in A just on age. Remember prior, we were doing on the entire data set. Here, I just want it on age. So if we go here, all right, so now if we come back here and run this, let's hope there will be no null values. All right, good. We've got a clean data set, and it's time to define our X and Y axes. Target survived, great. All right, let's go ahead and train test split. We need to segment our data into disparate sets. All right, now we're training the XGBoost. We're creating a variable, right, to hold our classifier, and I'm specifying a max depth of 4 and 50 estimators. All right, let's go ahead and train that. Great. Let's go ahead. We've seen this before. Run our data against test, and let's see how well we did. Not bad. Again, when you have a resume bullet point, like you put top 5%, I don't even know what it is. I just put like top 2%. And then when I'm asked to explain it, I'll actually bring my laptop and break this out, or I'll actually tell them, what I did. Like, all right, so in our accuracy, 86%, that's a fantastic number for this model. Not only that, this is a real model. This is something we could absolutely use in the real world. All right, so keep in mind on most of these Kaggle competitions, most of the models aren't ever used, right? For example, I'm sure if you're familiar with Kaggle at all, you're familiar with the Netflix competition. It was probably the thing that shot Kaggle to stardom, and models were so over-engineered that Netflix didn't use them. So Netflix just paid out that $1 million to get an idea because the final model that won the recommendation engine wasn't even used. That's not abnormal. Again, for you and I, we're doing it to create a bullet point, and really more important, we're doing it to take this and walk a prospective employer through what we did and how we did it. What were the things that made us score that high? And as you've seen through the course, that thing that makes you score high is going to be how clean your data is. All right? Let's wrap up what we learned in this section. In this section, you saw the importance of handling missing data correctly. You've heard me say it time and time again. Applied machine learning is all about data and very little about modeling. If you feed your model a nicely cleansed data set, you've won 90% of the battle. Additionally, don't let your models do the cleansing. You do it, and the results will often be much better than relying on the model. In this lesson, you learn how to save a model to disk. The term serialize is often used instead of saving, just different vernacular. I use Pickle often, and if you're always working in Python, it's a great way to save or persist your models to disk. You'll learn how to use importance scores in XGBoost and why you might not want to. Importance scores provide an indication of how useful or how valuable each feature was in the construction of a boosted decision tree within your model. The more an attribute is used to make key decisions within the decision tree, the higher its relative importance. In this section, you'll learn how to monitor your model's performance. You can view the results of each of your iterations of your model to find the best score. Additionally, in this section, you learn how to use early stopping to avoid overfitting. Early stopping is an approach to training complex machine learning models to avoid overfitting. In this section, you learn how to configure multi-threading support for XGBoost. Most of the time, you won't have to do anything. XGBoost will be configured for multi-threading out of the box. In this section, you learn the default hyperparameters from XGBoost and from scikit-learn. You'll get different mileage depending on your model, but I suggest you start off with max depth first. The second one I suggest is in estimators. Find a baseline using these two and then move on from there.